Welcome to section 2.3. As I mentioned in the first lecture, there's no multiplication between vectors, but there is something called the dot product. And this is the formula for the dot product of two vectors in R3. And that generalizes to R2, just take out that component, or R4, just add another component. So let's take a look at some examples here. We want to find u dot v. Now notice when we take the dot product of two vectors, we're actually going to get a number, not another vector. So this is, I multiply the x coordinates to get 6, and then I add on the product of the two y coordinates, which is -6, and finally add on the product of the z components, which is -2, and I add those together and I get -2. Okay, next one. I like to rewrite my vectors in component form, 1/2, 3, 1, and we're dotting with 4, -1, and since there's no k there, there's a 0 there. All right, and so I multiply the x coordinates, and that gives me 2, and I add the product of the y coordinates, and that's -3, and then plus 0 is -1. So again, take the dot product of two vectors, and you get a number. So here's some properties of dot. Dot is commutative, and in the right column, I've got examples of each property. Dot is commutative. There are two distributive properties. The way scalar multiples distribute into dot is the constant c can be distributed to u or distributed to v, not both. For example, in algebra, an analogous property would be 5 times xy is the same as 5x times y is the same as x times 5y, but you wouldn't distribute the 5 to both the x and the y. Contrast that with property 3, which is this distributive property where u dot v plus w does distribute u dot v plus u dot w. All right, property 4, 0 dot u is 0. So what's going on here? This 0 is a vector, and the second 0 is a scalar. So for example, if u is 1, 2, I can't dot with the number 0. I've got to be dotting with the vector 0. And when I do that computation, I get 0. And finally, property 5 is a nice way to get rid of square roots. We can think about u dot u as the length of u squared. So for example, over here, if I take u dot u, I get 1 plus 4, which is 5. Whereas if I take the length of u, I get the square root of 1 squared, which is 1, plus 2 squared, which is 4, and that gives me root 5. And sure enough, if I square that, I do get 5. All right, last thing on this page, angles between vectors. There are two formulas. Cosine theta is u dot v over length of u, length of v, and that just solves for the cosine, or you can actually go all the way and solve for theta by taking cosine inverse of both sides. And cosine inverse always returns an angle between 0 and pi, and that will be the angle that you seek. And a super important definition, two vectors are orthogonal if their dot product is 0. And another word for that is perpendicular. Okay, let's do an example. We want the angle between u and v. I'm going to start with the cosine of the angle between u and v. And it's best practice to write down a formula that you're going to use before you use it, both for your sake and the sake of the reader. And so if we take u dot v, on top we're going to get -1 minus 4 minus 9. And on the bottom, the length of u is the square root of 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9. And then the length of v, we multiply by the length of v, which is the square root of -1 squared, which is again 1, -2 squared, which is 2, plus -3 squared, which is 9. And so on top, I've got -14, and on the bottom, I've got root 14 times root 14, which is 14. So when I simplify, I get -1. And then theta is cosine inverse of -1, and that's an easy computation. That's just pi. Okay, vector projections. The projection of u onto v is given by this formula here. And what it is geometrically, it's the part of u that goes in the direction of v. So the projection of u onto v lies down here parallel to v. And the component of u orthogonal to v is the vector z equal to u minus the projection of u onto v. Now in my picture, I've got z dotted in over here, but if I write z in standard form, it's here. If I draw z in standard form, that is. And then we can see that we've decomposed u as the sum of two orthogonal vectors, the projection of u onto v plus z. Those two vectors are orthogonal and they add together to be u. All right, so let's do an example. In my picture here, this is the vector u and this is the vector v. So the first part, find the projection of u onto v. That's u dot v over v dot v times v. Okay, so let's just look up here at u and v. If I take u dot v, I get 14 plus 12. That's 26. V dot v is 4 plus 9. That's 13. And the vector v is 2, 3. So that's twice 2, 3, which is 4, 6. So that's the projection of u onto v. Let's draw that. That vector would be up here, lying on this line. So this is the projection of u onto v. And we can see, sure enough, if we drop a perpendicular down like this, that is the part of u that's going in the direction of v. So part B, find the component of u orthogonal to v. That's the vector I'm calling z, which is u minus the projection of u onto v. Okay, well that's 7, 4 minus 4, 6, which is 3, -2. Let's draw that. That would be about here. So this is z, and I can see that z is perpendicular to v. And if I add z together with the projection of u onto v, I do get u. Okay, let's finish up with a discussion about force and work. We know from physics and first semester calculus that work is force times distance if you're working in a line. Now, if you're working in 2D, you just need to be a little bit more clever about how you compute that number. So in my picture here, I only want the part of the force that's going in the direction of d. And so what I want is the work equal to the length of the projection of F onto d times the length of d. Well, the length of the projection is the length of F cosine theta, and then I multiply by the length of d. That's how I get this second formula you see down here. And the way to get the first formula, this one, is just to use that formula we had on the previous page about the angle between two vectors. Now, which formula are you going to use? Well, if you're given the force and the distance in terms of vectors, then you're going to want to use the first one, F dot d. But if you're given the magnitude of the force, the magnitude of the direction, and the angle between them, then you're going to want to use the second one. So in this example here, this 90-year-old man who's pulling a car with his teeth, we want to use the second formula. So we want work equals the length of F, length of d, cosine theta. Okay, we have a 200 Newton force, so the length of F is 200. The length of d, well, we're pulling this car 20 meters, so that's the length of d. And theta is 30 degrees, so cosine pi over 6, I like radians. Okay, so that's going to be 20 times 200 times root 3 over 2. And finally, that's going to be 2,000 root 3 joules. And there it is. Okay, and that is the end of this section.